This training is a basic introduction to pump hydraulics. It will cover theory of operation, some basic physics, and terminology specific to the pump industry. To begin, we will cover a brief history of the centrifugal pump. As a machine, the centrifugal pump has remained relatively consistent in design for over 300 years. The first pump was likely built in the late 1400s and was used as a mud lifting machine. The first true centrifugal pump with straight vanes was developed in Europe in 1687 for drainage. Eventually, curved vanes, which are more efficient, were developed and employed by engineers around 1851. Centrifugal pumps became prominent in the US in the early 1800s, and we have seen more widespread use in the last 75 years. To explain how the pump works, let's start with a volute or pump casing full of water. This would mean the pump is primed. As the engine or motor rotates the impeller, it forces the water to the outside of the casing or volute. As the water is forced to the outside, its velocity increases and the water at the center or eye of the impeller sees a drop in pressure. This drop in pressure creates what is referred to as a pressure differential between the water inside the pump case and the outside atmospheric pressure. The difference in pressure enables the atmospheric pressure to push water into the eye of the pump. The volute then guides the water in a specific direction while slowing it down. This increases its pressure or potential energy. Most, if not all, of the interesting physics happen with the impeller and volute and how they work together. The pump ultimately converts rotational energy from the impeller to kinetic or moving energy to the fluid. The amount of energy imparted to the liquid directly corresponds to the velocity at the edge of the impeller. The volute slows the fluid down and converts the velocity to pressure energy in the most efficient way possible. In the next few slides, we will cover pressure, vapor pressure, temperature, boiling point, specific gravity, the Bernoulli principle, and head. All of these concepts are critical to the function and application of centrifugal pumps. When discussing pressure, it is important to first establish what type of pressure we are talking about. The two types of pressure are called gauge pressure and absolute pressure. Gauge pressure is the pressure relative to atmospheric pressure, which is about 14.7 psi at sea level. This means a standard pressure gauge reading 0 is actually at 14.7 psi. Absolute pressure starts at a perfect vacuum and goes up from there. Where does 14.7 psi come from? The image to the right illustrates how atmospheric pressure works. As you may already know, the air in our atmosphere has mass. If we take 1 square inch of that mass from the Earth's surface to the edge of the atmosphere and apply Earth's gravitational force to it, we get 14.7 psi. Now it's time for a quiz. What is the absolute pressure of a flat tire at sea level? The answer is 14.7 psi. Tires are inflated at around 30 to 40 psi gauge, so 0 gauge equals atmospheric pressure. If you answered 0 psi, remember that the question asked for absolute pressure, not gauge pressure. The next important concept to review regarding pressure is vapor pressure. Vapor pressure is a liquid property related to evaporation. Technically, it is the pressure of the fluid when it reaches equilibrium at a given temperature in a closed container. The rate of evaporation and the rate of condensation are equal at the vapor pressure. The vapor pressure will increase as temperature increases, and it is also very dependent on the intermolecular forces within the fluid. The intermolecular force is why water tends to bead up and is why surface tension exists. In other words, vapor pressure varies with different fluids. The image to the right shows what is happening within water at room temperature compared to water that is boiling in an open container. For the left container, atmospheric pressure keeps bubbles from forming, which prevents molecules below the surface to escape and turn to vapor. Once the water reaches its boiling point, where vapor pressure equals atmospheric pressure, the molecules have enough energy to escape the fluid. Another way to describe vapor pressure is the pressure required to boil water at a given temperature. The greater the atmospheric pressure, the more heat or energy is needed to boil water. The opposite is also true. Water can boil in two very different ways. The most common way is to heat up the water until it reaches around 212 degrees Fahrenheit, like you would do on your kitchen stove. Another way to boil water is to lower the ambient pressure until the boiling occurs. This will happen at around 1/40th of atmospheric pressure when the water is 70 degrees Fahrenheit. To quiz your understanding, will water boil below or above 212 degrees Fahrenheit on the top of Mount Everest? The correct answer is below. Due to the high altitude, the atmospheric pressure will be less, so the required energy to reach boiling will be less than at sea level. The best way to describe specific gravity is the weight of the fluid. It is the ratio of the density of a substance compared to a standard substance, usually water. If the viscosity of the liquid is like that of water, specific gravity has no effect on pump performance, but it does drastically affect the power required to pump the liquid. It can also influence the onset of cavitation in a pump. Heavier liquids increase the pump's suction energy, so pumps with high suction energy levels, meaning high flow and lift, may experience cavitation damage. The definition of viscosity is a fluid's resistance to flow or shear. It is the internal friction of a liquid and is due to the cohesive forces of the fluid molecules. The units for viscosity are usually one of the following: centipose, centistokes, or SSU. In most cases, the viscosity is related to temperature, meaning that as the liquid warms up, its viscosity decreases and it flows easier. Due to the fluid having more internal friction, the fluid will resist movement, causing flow, head, and efficiency to decrease, and horsepower required to increase. Bernoulli's principle is one of the most important concepts related to the function of centrifugal pumps. It is defined as the increase in speed of a fluid occurring simultaneously with a decrease in pressure of that fluid. There are many everyday examples of the Bernoulli principle. An aircraft wing creating lift is probably the most famous example. There is also the shower curtain that gets sucked in when the shower is turned on, chimneys creating a vacuum causing the fire to thrive on a windy day, and using your thumb as a hose nozzle to water the garden. This principle leads to what's called the Venturi effect. The Venturi effect is covered in more detail in a separate presentation that covers our Venturi-style priming systems. The pump volute gradually increases in internal area from the cut water to the discharge. This increase in area slows the liquid velocity down and increases the liquid pressure. As the images show, one side of the impeller sees far more pressure than the opposite side. To remedy this on high-pressure pumps, a double volute can be used. Double volute casings have two cut waters located 180 degrees apart from each other to balance the radial loads. Pioneer has utilized a double volute design in several high-pressure pumps. The term most commonly heard and critical to understand in the pump industry is head. Head is the measurement of the kinetic energy a centrifugal pump creates. It is directly related to the velocity that the liquid gains when traveling through the pump. It literally is the measurement of the height of a liquid column shot straight up from the volute discharge. The term head is used in place of basic pressure due to the fact that the pressure will change if the specific gravity of a liquid changes, but the head will not change. To get head from psi, multiply psi by 2.31 and divide the product by the specific gravity of the fluid. The image to the right shows static head values for a suction lift application. Total static head is the distance between the surface of the fluid on the suction side to the fluid surface on the discharge side. Those surfaces are where atmospheric pressure is acting. Pipes or hoses introduce many other factors including friction and entrance losses, but all of these can be described in terms of head. All of the head terms are added together to get the total dynamic head of the system. Centrifugal pumps are often put into applications where the suction fluid is above the pump center line. This application puts head or energy into the system due to the help of gravity. This is commonly referred to as a flooded suction application. In flooded suction applications, the amount of work the pump must perform is much less due to the total static head distance being smaller than suction lift applications. Friction losses are still a factor, but gravity does most of the work on the suction side. Due to the constant gravity-fed supply of fluid, automatic priming systems are not required in these applications. Now that the basic hydraulics have been covered, let's discuss the three main types of centrifugal pumps. The first type is the axial flow pump. These pumps are used in high flow and low head applications. This includes flows up to 300,000 gallons per minute and heads up to around 30 feet. Radial flow pumps refer to the modern centrifugal pump. They are designed to produce higher pressures or head and lower flows than axial pumps. The last type of centrifugal pump is a peripheral pump, also known as turbine or regenerative pumps. These pumps are used where high pressure is needed and flow requirements are relatively low. Unlike radial flow pumps, peripheral pumps can transport fluids with high gas content, but they lose to radial pumps in efficiency. Multi-stage pumps are also technically considered centrifugal pumps, since they are made up of multiple enclosed impellers in series inside a common casing. They have the unique ability to produce higher and higher pressures with the addition of more stages, all while being highly efficient. Due to the tight clearances and multiple impellers, they are usually restricted to clean water applications. Positive displacement pumps operate with a series of working cycles. Each cycle encloses a certain volume of fluid and moves it mechanically through the pump into the system. Depending on the type of pump and the liquid being handled, this happens with little influence from the back pressure on the pump. They are used in a wide range of applications, from services where a specific amount of liquid must be moved into a system to heavier duty services where the liquid is simply too viscous to be handled by a centrifugal pump.